Welcome to the lecture for DES 2, Unit 3, Dimensioning Review, Dimensioning and Tolerancing Practices by Todd Frazee. Technical drafting involves the science of geometrics, or the science of specifying shape, location, and tolerances of features of an object in graphic form. Dimensions are the information added to orthographic representations of the object to define size and tolerance of the features on an object. Full definition of an object in technical drafting requires first graphics, second dimensions, and third words in the form of notes. A well-dimensioned drawing will fully define the part by communicating the size and location of each feature. Two basic criteria can be used for dimensions on drawing views. First, the basic size and location of part features must be defined. Second, the details of construction for manufacturing the part must be defined. Units of measure throughout the world vary. Internationally, metric or SI units are used, but in the US, units are in inches unless otherwise specified on the drawing. As a general rule, once an object reaches 72 inches in length, the units will switch to feet and inches. But this is also industry specific. The aircraft industry, by example, maintains units in inches regardless of feature size. The most common metric unit used on technical drawings in the United States are millimeters, abbreviated as mm. Metric drawings in the US must be labeled metric or contain a note to the effect all dimensions are in millimeters. And dual dimension schemes are used by some companies where both inch and millimeters units are displayed on dimensions, but this is not supported by ASME standards as of today. There are two dimensioning methods common in industry where dual dimensioning schemes are used. There is position, which is the first one, where the primary and the alternative unit value is separated by a line or a slash, as displayed on the right. The second method is called the bracket method, where the alternative units are displayed in brackets, as shown on the right. In my experience, the second method, brackets, is the more common of the two methods, but the author of our text discourages the use of dual dimensioning schemes. Angular dimension units. There are two unit systems used for angular dimensions. The first is decimal degrees, abbreviated as DD, and appears as displayed on the right. Or in the form of degrees, minutes, and seconds, abbreviated DMS, as shown as the second example on the right. In the DMS system, degree is divided just like time, with 60 minutes in a degree, and each minute is comprised of 60 seconds. Note that if in the DMS system is used and the angular dimension is less than a degree, Zeros precede each unit, like in the third example on the right. In my experience, decimal degrees is more common on modern drawings, but the DMS system can be common on legacy drawings. Dimensions. What are dimensions? A dimension is a numerical value that defines a feature. Size, shape, location, surface texture, geometric characteristic, balloon number 1 is highlighted by balloon number 1 is the most basic form of dimension, defining a feature width of 1/2 inch or 0.5, or in machinist vernacular, 500 thousandths. ASME standards define specific standards for the elements of dimensions. When using decimal inch, the text is to be the decimal equivalent of 1/8 of an inch, which is 0.125 as shown as item A on the right. The space between the line of text is to be the decimal equivalent of 1/16 of an inch, which is 0.0625 inches, or as a machinist would say, 62 thousandths 5/10. Values of less than 0 are not preceded with a 0, as shown in the example on the right as item B. If space for the text is limited, the value or arrows may be reconfigured, as shown in items B, C, and D in the image on the right. Millimeter dimension standards. Elements of millimeter dimension standards. The text is to be 3 millimeters, as shown on the right as item A. The space between lines of text is to be 1.5 millimeters. And values of less than 0 are preceded by a 0, which is a flag that the drawing is in metric. An example is shown. And like with the inch standards, if space for text is limited, the value and/or the arrows may be reconfigured in any of the configurations shown as B, C, and D on the right. Basic dimensions. Basic dimension is a numerical value that defines the theoretical actual size of a feature and is denoted by the value being enclosed by a box, as shown in the image on the right. The value in the dimension does not denote a tolerance, and the tolerance is derived from a related geometric control frame. Reference dimensions. Reference dimensions are numerical values enclosed in parentheses, not to be used for fabrication, as shown in the image to the right. Reference dimensions do not include tolerance and are for informational only in nature. The part definition must be taken from dimensions not marked as reference. Reference dimensions are often included for convenience, such as material planning, or for clarification on multi-sheet drawings, where the controlling dimensions may be on another sheet. Dimension lines. The dimension line is a thin, solid line that shows the extent and direction of a dimension, as shown in the image on the right. The line is broken by the dimension number. Arrows. Arrows are symbols placed at the ends of dimension lines to show the limit, dimensions, leaders, and cutting planes, as shown in the image on the right. Arrows are uniform in size, regardless of the size of the drawing. Arrow style. Arrow style may be such that they are 1/8 of an inch or 3 millimeters long, and the width of them should equal 1/3 of the length of the arrow, as shown in the image on the right. And the arrows may be filled, closed, or open. As shown in the lower right, but all of the arrows should be the same style throughout your document. Extension lines. A thin, solid line that runs perpendicular to the dimension line indicates which feature is associated with the dimension. See the image to the right, which highlights an extension line. Visible gap. A visible gap should be visible between a feature and the end of an extension line, as shown in the image on the right. The gap should be 1/16 of an inch or 1.5 millimeters. Leader line. It's a thin, solid line used to indicate a feature with an associated dimension, note, or symbol, as shown in the image on the right. Leader lines terminate in an arrow to denote the associated feature. Text occurs on the end of a short horizontal line on the opposite end of the leader line, which is called a shoulder. Limit of size. A limit of size dimension denotes an acceptable size range by displaying two numbers, as noted on the right. The larger number represents the largest the feature can be and be acceptable, or maximum material condition, abbreviated as MMC. The smaller number represents the smallest the feature can be and be acceptable, or the least material condition, abbreviated as LMC. Plus and minus dimensions. Plus and minus dimensions denote the allowable positive and negative variance from a specified dimension value, as shown in the image on the right. The tolerance on a plus or minus dimension can vary from each other on a given drawing, and the tolerance can be either symmetric or asymmetric range from the nominal dimension given. The diameter symbol. The diameter symbol is a symbol appearing like a zero with a slash through it, the center, and it precedes a diameter dimension, and it's actually derived from a Greek letter. Radius symbol. The radius symbol is a symbol appearing as an uppercase R, and it precedes a radius dimension as shown in the image on the right. Tolerance. Tolerance is the amount that a particular dimension is allowed to vary and be acceptable. A general tolerance for all dimensions otherwise specified can be communicated in a note, as shown on the right, and can be often found in the drawing title block. Datum. A datum is a theoretical exact point used as a common reference for dimensions. In the example shown on the right, the left bottom edges of the part are the datums with a common origin where they meet in the corner. All dimensions referencing the common edge. Datum selection is critical to communicate the design intent and control the tolerances according to that intent. Size dimensions. Size dimensions are concerned with physical sizes of features. In the example shown on the right, uses horizontal size dimensions to describe width, vertical size dimensions to describe height and depth, a diameter dimension to define the size of the hole, and a radius size dimension that defines the external radius. Location and orientation dimensions. Location dimensions are primarily concerned with horizontal and vertical position of features in relation to the dimension references. In the example on the right, dimension A defines the horizontal position of the corner where the angle begins, and dimensions B and C define the position of the horizontal and vertical position of the center of the hole and external radius. Orientation dimensions are concerned with angular orientations of features, such as the example on the right. Coordinate dimensioning. Coordinate dimensioning is a scheme where the position of information is given as x and y coordinate distances from the origin, as in the example on the right. Arrows and dimension lines are optional with this method. The size of the holes also may be defined in tabular form using letters to denote corresponding holes, as is shown in the example on the right. ASME standard practices. ANSI, and later ASME, has developed ASME Y14.5 standard practices to guide drawing clarity. The standard involves the placement of dimensions, depends on the available space. When laying out dimensions, follow these steps for placement order. If dimensions and arrows will fit, they should both go between the extension lines, as shown in example A on the right. If there is room for the dimension, but not arrows, place the dimension between the extension lines and the arrows outside the extension lines, as is in item B on the right. If there's room for the arrows, but not the dimension value, place the arrows between the extension lines and the dimensioned value on the outside, as in example C on the right. And finally, if there isn't room for either dimension element, place them both outside the extension lines, as shown as item D. Spacing. ASME Y14.5 has specific standards for spacing dimensions, both from the object, but also from other dimensions. The minimum distance for the first dimension and the object is 10 millimeters or 3/8 of an inch. Each dimension is to be spaced a minimum of 6 millimeters or 1/4 inch apart. And extension lines should extend 2 to 3 millimeters or 1/8 of an inch beyond the last dimension line as shown on the right. Grouping dimensions. Grouping dimensions. Dimensions should be grouped for uniform appearance as shown on the right. The 40 millimeter and 50 millimeter dimensions are grouped and aligned with each other in the example. Staggering. Staggering dimensions. Dimensions should be staggered where there are several parallel dimensions as shown in the image on the right. We have several diameters and several heights that would be all on the same plane, so that each dimension, smaller to bigger, is staggered farther away from the part. Extension lines. Extension lines are used to dimension one of the or more features and are typically drawn perpendicular to the dimension lines, but they may be drawn at an angle if space is limited, as shown in the example on the right. Although this method would be highly discouraged, and it'd be more fitting to have an alternative view so that you can avoid this method. Limited length or area. The area or length of a process or surface treatment may be demonstrated with a chain line, as in the example on the right, which has a zone designated for application of a label. Dimensional reading direction. The reading direction of all dimensions in note text must be oriented unidirectional such that it's read parallel to the bottom of the drawing, as shown in the example on the right. View dimensioning. View dimensioning guidelines state that dimensions are to be kept outside of the boundaries of the views when practical. Repetitive features. The symbol X can be used to reduce the number of dimensions needed for repetitive features by indicating the number of instances. The number of instances is followed by the X and precedes the dimension text, as shown with the 4 times diameter 0.375 pattern defined in the example. This concludes part 1 of this lecture. Please continue to part 2.